Welcome. This is a video presentation of A Universe from Itself, the Geometric Mean Expansion of Space and the Creation of Quanta, Part 2, the Initial Values of the Universe. Based on the observations discussed in Part 1, we will now work under the assumption that the universe is undergoing a geometric mean expansion. We are going to look at the initial conditions of the universe, the time when expansion started. The age of the universe, T sub O, is given as R sub H divided by 2C. This is the inverse of our value for the Hubble constant. We calculated earlier that small time, T sub S, is given by this equation here. We're going to set the age of the universe, T sub O, equal to small time. We're going to plug in our value for T sub O, R sub H over 2C, and equal to our term for small time. We'll take our equation where T sub O, the age of the universe, was equal to the small time. We do the algebra, and we find the radius of the hyperverse at this point in time is equal to 2 Planck lengths. Therefore, the initial radius of the universe, R sub I, is equal to 2 Planck lengths. Let's look at the initial time. Taking our equation for the age of the universe, we've determined that the initial radius was 2 Planck lengths. We'll take this value of the initial radius and plug it in as RH. We do the algebra and we find the square root of big G times h bar over c to the 5th. This is the initial time, and it's equal to the Planck time. The energy of the universe is given by this equation. We know that R sub H initially was 2 Planck lengths. We'll insert it into the equation for energy, and we discover, after a little bit of algebra, that we get the square root of c to the 5th times h bar over g divided by 2. That's equal to the Planck energy divided by 2. Therefore, the initial energy is the Planck energy divided by 2. Similarly, for the mass of the observable universe, we take our value for mass, and we know that R sub H initially was 2 Planck lengths. Substituting the 2 Planck lengths into the equation, doing the math, we find that the initial mass is equal to the Planck mass divided by 2. So far, we've calculated these initial conditions. The initial radius was 2 Planck lengths. The initial time was the Planck time. The initial energy was the Planck energy divided by 2. And the initial mass was the Planck mass divided by 2. Let's look at angular momentum. But first, we're going to look at linear momentum. That's straight line momentum, and it's the product of mass times velocity. Angular momentum is the momentum related to spin, and it's the product of the moment of inertia and the angular velocity. L is our angular momentum. I is our moment of inertia, and omega is the angular velocity. The moment of inertia is equal to the mass times the radius squared. The angular velocity is equal to the tangential velocity divided by the radius. So if we take our term for I and omega and plug it into our equation for L, we find that L, the angular momentum, is equal to the mass times the radius times the tangential velocity. In the case of our ice skater here, in this situation here, A, her arms are outstretched and she spins with a certain velocity. If she pulls her arms in, her mass is the same, but her radius has decreased, the mass being closer to the center of rotation, and it's easier for her to turn. She spins more quickly, and the reason she does is because the angular momentum is conserved. So let's calculate the initial angular momentum. We know the angular momentum is equal to m times r times the tangential velocity. Our initial mass is the Planck mass divided by 2. Our initial radius is 2 Planck lengths. And the tangential velocity is given by the square root of 2 times c. And this value we see is constant from our work in the time paper. Doing the math gives us the square root of 2 times h bar. Therefore, the initial angular momentum is the square root of 2 times h bar. Let's look at rotational kinetic energy. That equation is given by 1/2 times the moment of inertia times omega squared. We plug in our value for the moment of inertia, m times r squared, times our value for omega squared, which is the tangential velocity divided by the radius squared, and we get 1/2 m v sub t squared. We got this equation in the time paper. We'll plug in our values. The initial mass, tangential velocity is a constant, and we find that the kinetic energy of rotation is equal to the initial energy. The period of rotation is determined by taking the circumference of the circle and dividing it by its tangential velocity, its rim speed. The initial period of rotation, t sub I, would be given by 2 pi r divided by v sub t, the tangential velocity. We know that the radius is 2 times the Planck length, and again, our tangential velocity is a constant at the square root of 2 times c. And we get the 2 times the square root of 2 times pi times this term here, which is the Planck time. Therefore, the initial period of rotation is 2 times the square root of 2 times pi times the Planck time. Frequency is the inverse of period. So the frequency, the initial frequency, is 1 over 2 times the square root of 2 times pi times the Planck time. Of interest is the Schwarzschild radius. It's given by this equation. Mass, if we plug in our value for the initial mass, we find the Planck length. Therefore, the initial Schwarzschild radius was equal to 1 Planck length. The current Schwarzschild radius can be calculated using the same equation, 2g times the mass of the universe divided by c squared, and we get 1/2 the radius of the hyperverse. The initial Schwarzschild radius was 1 Planck length. The Schwarzschild radius in general is 1/2 times the radius of the hyperverse. This value here is 1/2 of the initial radius, which was equal to 2 Planck lengths. So let's summarize the initial values. The initial radius was 2 Planck lengths. The initial time, the Planck time. The initial energy, the Planck energy divided by 2. The initial mass, the Planck mass divided by 2. Initial angular momentum, square root of 2 times h bar. The initial period of rotation, 2 times the square root of 2 times pi times the Planck time. The initial frequency, 1 over that value, and the initial Schwarzschild radius was 1 Planck length.